Hey there. Tonight, we'll take a slow and quiet journey through our solar system, not in search of adventure, but in search of stillness. From the warmth of the sun to the cold silence of the outer giants, each world has its own story, its own rhythm. Let's drift from planet to planet, moon to moon, absorbing quiet facts, timeless motion, and distant light. If you find comfort in these kinds of journeys, feel free to like, subscribe, or share your reflections in the comments. Let's begin the grand tour. The sun does not rise in space. It does not set. It simply exists, a constant, undimming sphere of nuclear stillness, radiating in every direction without pause or preference. From a distance, it seems calm. No flares, no eruptions. Just light, steady and ancient, crossing the dark with perfect indifference. We call it a star, but it is not like the stars we see at night. It is near, so near that every second of our existence, every cell of warmth on our skin, every whisper of weather on Earth is tied to it. And yet, we rarely think about what it is. A self-regulating fusion engine, 4.6 billion years old, with another few billion years of patience left. Its core, a place we'll never reach, burns quietly at 15 million degrees Celsius, fusing hydrogen into helium in a process that began before life on Earth and will continue long after we're gone. The photons born in that core will take tens of thousands of years to reach the surface, bouncing through dense plasma, diffusing slowly like a thought trying to find form. When they finally emerge, they make the journey to Earth in just over 8 minutes. All our color, all our warmth arrives this way. A delayed whisper from a star that thinks in epochs. We orbit it not by choice, but by gravity. A curve in space-time so subtle we call it circular, though it is not. The orbit is elliptical, but nearly round, maintained by a balance of motion and pull, speed and fall. The sun is not silent, but its sound cannot travel. In space, there is no medium for vibration. Yet inside, it hums. A resonant sphere whose oscillations ripple through its vast body. Helioseismology, the study of these internal waves, reveals clues about its inner structure, like ultrasound for a star. Its surface, known as the photosphere, is not solid. There is no true edge, only a thinning of plasma, a gradual fading of light until it escapes without being scattered. The photosphere boils with convection cells, granules, vast columns of rising and falling gas, each the size of continents, forming and dissolving in minutes. Sunspots appear here, darker and cooler regions where magnetic fields are tangled and strong. These spots follow an 11-year cycle, waxing and waning like a breath the sun takes over decades. They're not random. They follow bands of latitude, migrate toward the equator, and then disappear, only to return again. Above this lies the chromosphere, a layer of spicules and filaments, pinkish during eclipses, rarely seen. And farther still, the corona, the sun's crown, strangely hotter than the layers beneath it, millions of degrees compared to thousands. This inversion defies intuition, and although theories abound, magnetic reconnection, wave heating, we still don't fully understand why the outermost layer is the most energetic. During total solar eclipses, the corona becomes visible to the naked eye, pale and ghostly, stretching in threads and streamers far into space. From it, the solar wind escapes. This wind is not wind in any earthly sense. It is a stream of charged particles, electrons, protons, ions, moving outward at speeds up to 800 kilometers per second. This wind fills the solar system with invisible breath. It defines a region called the heliosphere. a vast bubble in the interstellar medium carved by the sun's influence. Every planet, moon, asteroid, and comet exists within this domain. Even distant Voyager probes, now in interstellar space, once felt this wind against their sensors. The solar wind also shapes planetary atmospheres. It helped strip Mars of its air, sculpts auroras on Earth, and pushes against magnetic fields like an unseen tide. Sometimes this wind flares into coronal mass ejections, massive outbursts of plasma and magnetic field, which, when aimed toward Earth, can disrupt satellites and power grids. But out here, on the slow journey through space, it is not a threat. It is just another current in the ocean of space. The sun's magnetic field flips every 11 years, part of a cycle that resets polarity across the solar system. North becomes south, then returns. It is a gentle kind of chaos, organized, yet unpredictable in detail. Solar storms and calm years follow one another like seasons without weather. We see the sun as a flat disk, 400 times larger than the moon, but also 400 times farther away, which is why they appear the same size in the sky. A coincidence of geometry that allows eclipses. A coincidence that also reminds us the solar system is not just a physical place. It is a geometry of alignments and ratios, balances and near misses. From Earth, the sun seems eternal, but it too will change. In 5 billion years, it will expand into a red giant, swallowing Mercury and Venus, possibly Earth. Its outer layers will drift away, leaving behind a white dwarf, a dense core glowing faintly in the dark. But that is not our concern tonight. Tonight, the sun is steady, burning, breathing, holding everything in motion, not with force, but with gravity, the quiet language of mass and time. And so, before we drift outward, it's worth remembering that every orbit begins here. Every planet, every moon, every piece of ice and rock dances because this one object exists. The sun is not just the center of the solar system. It is the beginning of movement, the cause of seasons, the anchor of calendars. It gives no instruction, no signal, just presence and light. When viewed from afar, from a place without atmosphere, without interference, the sun does not flicker. It remains fixed, consistent, quietly immense. But its influence is not uniform. Across the solar system, the intensity of sunlight drops with distance. On Earth, it is strong, defining our days. But by the time you reach Jupiter, it has dimmed to a quarter of its strength. At Neptune, it is little more than a bright star. Still powerful, still dominant, but distant, both in warmth and in meaning. Yet the sun's reach is not limited to light. It extends through its gravity, through the solar wind, through magnetic resonance. It holds the orbits of the outer planets, nudges comets, and even exerts a gentle drag on the interstellar medium. It defines the heliosphere, an invisible bubble shaped like a teardrop where the sun's particles push back against the galaxy's ambient dust and radiation. This boundary, called the heliopause, is not a wall. It is a region of transition where the solar wind slows, mingles, and fades. Voyager 1 crossed it in 2012, followed by Voyager 2 in 2018. After more than 40 years of flight, these spacecraft still send signals, faint and slow, powered by thermoelectric decay. They carry with them a message, the golden record, a human attempt to explain ourselves to no one. But long before they reach the edge, they pass through another realm, the region where the sun's gravity, though weak, still binds. This sphere, the gravitational domain, extends far beyond the heliosphere. In theory, the sun's pull reaches endlessly, though in practice, it is overtaken by galactic tides and stellar drift. Still, It holds the Oort cloud, a hypothetical shell of icy bodies far beyond the planets, barely tethered, barely orbiting. These distant comets may take millions of years to complete a circuit. Their motion, like time itself at these distances, is difficult to define, but even they owe their trajectories to the Sun. The Sun, then, is not a single object. It is a system of fields, layers, gradients. It radiates not just light, but structure, a scaffolding of temperature, pressure, and motion. Closer in, near the planets, this scaffolding becomes more intricate. Mercury, for instance, is not simply close to the Sun. It is embedded in the Sun's magnetic field. It experiences radiation fluxes, temperature cycles, and orbital resonances that are unlike any other world. Its proximity reveals the Sun's variability, how solar storms can change surface conditions, how even the solar tide affects planetary spin. But that is for the next chapter. For now, the Sun remains our anchor. It is not a character in this story. It does not act. It simply continues. A sustained release of energy from a collapse long past. A memory of a cloud of gas, compressed by gravity, heated by friction, lit by fusion. The beginning of the solar system was not an explosion, but a condensation, a narrowing of possibilities. Over time, the core ignited, the disk flattened, planets coalesced, all of it guided by the Sun's formation. And even now, billions of years later, that shaping continues. The Sun's gravity is not just a downward force, it is a path definer. Planets do not fall into the Sun because they are moving forward, as they are pulled inward. This balances orbital motion, a constant falling that never arrives. And this motion is not smooth. It contains perturbations. Jupiter pulls at Saturn. Venus tugs slightly at Earth. Over millennia, these gravitational whispers reshape orbits, change inclinations, alter distances. But the Sun remains the central mass, the fixed point in a system of loops and ellipses. Even time itself is tied to the Sun. Our seconds, minutes, days, and years are based on its rhythm. A day is the Earth's rotation relative to the Sun. A year is one orbit around it. Leap years, solstices, equinoxes, all are calibrations of our relationship to this one object. It gives us not just energy, but temporal structure. And that structure extends into memory, myth, architecture. Temples aligned with solstices. Calendars etched in stone, sundials, agricultural rhythms. The Sun shapes not only motion, but meaning. It was worshipped not because it demanded it, but because it could not be ignored. In sleep, we do not see it, but it still defines the boundary between day and night. And in this story, a story meant not to awaken but to calm. The Sun is less a furnace and more a foundation, a quiet origin, a constant pressure, a center that does not speak. If we could stand on a platform outside the solar system and look back, we would not see the planets clearly. We would see their orbits, faint rings of dust and light, illuminated by the Sun. We would see the zodiacal light, scattered sunlight reflecting off interplanetary particles, forming a faint cone along the ecliptic. We would see solar radiation interacting with comet tails, pushing them away even as they fall sunward. We would see the Sun not as an object, but as an influence. And that influence is what connects every stop in this journey. It is not just light that binds the solar system. It is inheritance. All planets, moons, and rocks formed from the same rotating disk. They are siblings in a way, different outcomes of the same beginning. The Sun does not remember this, but the structure it created does. The distances, the masses, the angular momenta, all of them echoes of the solar nebula. Tonight, we travel outward from that origin, knowing that every place we visit owes its path to this single presence. And as we leave the inner corona, passing the orbits of space probes and debris, we approach the first planet, Mercury, a small, scarred world, the closest to the Sun, and yet often overlooked. But before we go there, one last observation. The Sun, while vast, is only an average star, G-type, middle-aged, not young, not old, not too bright, not too dim. And yet for us, it is everything. Its mediocrity is our fortune. Its stability allows for complexity. Its gravity holds our story in place. Not with urgency, not with drama, but with quiet, ceaseless pull. Mercury is not the hottest planet, though it is the closest to the Sun. Heat, it turns out, is not only about proximity, it's about what is retained. And Mercury retains very little. It has no atmosphere to speak of, no blanket to trap warmth, no clouds to distribute energy. What light it receives, it reflects or radiates quickly, leaving its nights unimaginably cold. On its sunlit side, the surface can reach 430 degrees Celsius. On the dark side, it can fall below minus 180. This staggering contrast plays out across a world smaller than some moons. Its days are long, longer in fact than its year. A single solar day on Mercury lasts 176 Earth days, while its full orbit around the Sun takes just 88. This strange rhythm arises from a 3.2 spin-orbit resonance, where the planet rotates 3 times for every 2 revolutions. As a result, a sunrise on Mercury is not followed by a quick noon and sunset. The Sun climbs slowly, lingers, then appears to reverse direction briefly before resuming its path. Shadows stretch and fold across a landscape of rock and silence. Mercury's surface is battered, ancient and largely unchanged. There is no weather, no erosion from wind or water. What has struck it remains visible. Craters dominate, ranging from tiny pits to vast impact basins hundreds of kilometers wide. One of the largest, the Caloris Basin, spans over 1,500 kilometers, ringed by mountains raised by shock waves from the impact. The interior of Mercury is dense, the densest of all planets when adjusted for compression. Much of its mass is a large metallic core, surrounded by a thinner mantle and crust. This iron-rich heart generates a weak magnetic field, a rarity among terrestrial planets without tectonic activity. It is believed that some portion of the core remains liquid, and the slight field it creates interacts with the solar wind, forming a tiny magnetosphere. But this magnetic bubble offers little shelter. Charged particles from the Sun strike directly, liberating particles from the surface, forming a tenuous exosphere. Not an atmosphere in any conventional sense, but a temporary cloud of atoms knocked loose by sunlight and solar wind. Sodium and potassium, magnesium and calcium. These elements shimmer briefly in the near vacuum, then are lost to space. Unlike Earth, where the sky is full of scattering air and color, Mercury's sky is black. Even at noon, the stars remain visible. The Sun, nearly 3 times larger than on Earth, dominates the sky, but its light is unfiltered, harsh, white, casting inky shadows. There is no blue sky, no twilight, just light and rock, and time, because time behaves differently here. Not in the relativistic sense, though that too can be measured, but in the sense of rhythm. Without wind, without rain, without tectonic movement, Mercury's surface changes only through impact. Each crater is a record, a fixed moment of violence from long ago. Walking across the surface, if one could, would be walking through frozen time. There are no rivers to erase paths, no vegetation to cover scars, only dust, gravel, stone, and the occasional cliff. Long, sinuous scarps that stretch for hundreds of kilometers, evidence of a world that shrank as it cooled. These cliffs, called lobate scarps, are thought to be thrust faults, formed as the planet's interior contracted. Imagine a sphere cooling slowly, its outer shell wrinkling like the skin of a drying fruit. The result is a series of abrupt drops and rises in terrain, jagged and steep, preserved by the absence of change. Mercury has no moons. It circles the Sun alone, without companionship or significant tilt. Its axial tilt is almost zero, just a third of a degree, meaning there are no seasons. The poles, however, hold something unexpected. In some of the deepest, darkest craters near the poles, where sunlight never reaches, water ice has been detected. Not snow, not frost, but hard, reflective deposits likely delivered by comets or locked in place for billions of years. These cold traps are among the few places on Mercury where silence meets stability and stability meets preservation. Messenger, a spacecraft that orbited Mercury from 2011 to 2015, mapped the surface in detail, revealing variations in composition, color, and topography. It discovered hollows, irregular depressions with bright interiors and halos that may be signs of volatile elements sublimating in the heat. This is a world that continues to surprise, despite its small size and proximity to the Sun. Its silence is not emptiness, it is resistance, a kind of stubborn existence that has endured bombardment, radiation, and time. Mercury is often passed over in favor of flashier planets, the red sands of Mars, the storms of Jupiter, the rings of Saturn. But in its own way, Mercury is the most distilled expression of a rocky world. No adornment, no layers of air or water, just mass, orbit, and sunlight. It holds no illusions, it does not shimmer. It reflects what it is. And in that stark honesty, there is a kind of clarity. As we leave its orbit, accelerating outward, Mercury remains close to the Sun, circling steadily, never quite breaking free, never quite consumed. Its dance is locked, its timing precise. A planet that lives not in color, but in contrast, not in sound, but in record. And still, it turns. There is a rhythm to Mercury's silence, not of movement, but of waiting. Unlike Earth, with its shifting crust, or Jupiter, with its perpetual storms, Mercury holds still. Its orbit carries it quickly around the Sun, but its surface remains almost motionless. The sunlight crawls across its landscape, not in seconds or minutes, but over weeks and months. A single sunrise can take a quarter of an Earth year to unfold. This slow passage of light and shadow stretches time in the imagination. It makes Mercury feel like a place outside of sequence, a relic more than a participant. It has no air to transmit sound, no clouds to drift, no erosion to smooth its features. What is present now is much like what was present hundreds of millions of years ago. The craters still rimmed in sharp relief, the scarps still rising without weathering. Even the regolith, the fine dust that coats the surface, is static, moved only by micrometeoroid impacts or solar radiation pressure. Each grain holds its place in a record that never closes. There are no days as we know them, no breezes, no color shifts in the sky. There is only brightness and dark, heat and cold, presence and absence. But even within that contrast, Mercury changes. Not visibly, not quickly, but in the long, slow interaction between the Sun and the planet's iron-rich core, there are subtleties. The magnetic field, though weak, suggests motion beneath the crust. Not plate tectonics, but thermal activity, the slow release of internal energy, the final murmurs of a once more fluid interior. And above it, The exosphere changes too, fluctuating slightly with the sun's activity, swelling during solar storms, receding in quiet. These delicate atmospheric traces are temporary, easily lost, but their presence reminds us that even stillness is layered. Mercury's geological past is complex. There are signs of ancient volcanism, now long dormant. Plains smoothed by lava flows, ridges formed by cooling contraction. The absence of erosion means these features endure, barely softened. In some regions, ghost craters can be seen, remnants of older impacts buried by younger flows. These palimpsests of rock tell stories not in words, but in overlaps. Like faded writing on a scroll reused over time, each surface on Mercury contains traces of what came before. Light here behaves differently, not in its physics, but in its experience. With no air to scatter it, shadows are absolute. The line between sunlit terrain and night is sharp. No dusk, no gentle fade. Surfaces in direct sunlight are blinding. In shadow, they fall into pure black. The eye cannot adjust easily. Cameras sent by spacecraft must calibrate carefully to capture detail. From orbit, Mercury presents a visual contradiction. A world close to the source of light, yet cloaked in the visual austerity of a moon. One might expect golden hues, but instead sees muted greys and browns. The surface is low in iron oxides, the compounds that give Mars its red, and instead contains silicates, sulfides, and unexpected chemical fingerprints. These elemental clues hint at a formation story that is still debated. Did Mercury once have a thicker mantle, stripped away by a massive impact? Or did it form closer to the Sun, where conditions favored a metal-rich composition? The theories persist, but none fully explain its density, its structure, and its magnetism together. Even in its quiet, Mercury resists easy answers. And this resistance is part of its fascination. It does not display, it does not advertise, it endures. As we leave its orbit and begin the journey outward, the contrast between Mercury and its neighbor becomes immediate. Venus, shrouded in clouds, is almost the opposite in every way. Where Mercury is bare, Venus is hidden. Where Mercury's day is long but comprehensible, Venus's is disorienting. Where Mercury reflects what it receives, Venus traps and transforms it. But before we arrive, there is one last glance backward. From a position near the boundary of Mercury's orbit, the Sun still dominates the view. Mercury itself is a dark crescent, partially illuminated, moving slowly against the starry backdrop. There are no moons to trail it, no rings, no haze. Just the curve of a cratered world sliding steadily through sunlight. And in that view, simple, unadorned, there is a kind of clarity. Planets do not need to be large or colorful to hold weight in the solar system. They exist by mass and orbit, by gravity and motion, by silence and time. Mercury reminds us of this. It reminds us that presence is not performance, that proximity to energy does not guarantee warmth, that the absence of air does not mean absence of meaning. As the spacecraft, or imagination, drifts farther out, the Sun grows slightly smaller. The light still strong, but now more angular, more defined. Ahead lies a planet wrapped in reflection, hidden in brightness and shaped by pressure. Venus awaits, a world where time moves slowly, heat accumulates endlessly, and clouds never part. But that will be the next chapter. For now, Mercury continues its path, silent, ancient, and always just a little too close to the light. Venus appears bright in Earth's sky, often called the morning star or the evening star. But this brightness is misleading. It is not a sign of warmth or invitation. It is reflection. Venus is wrapped in a thick, unbroken blanket of clouds that bounce sunlight with great efficiency. The clouds hide everything beneath them, not just from telescopes, but from centuries of wandering. For most of human history, we did not know what lay under the brightness. Some imagined oceans, forests, perhaps even life. But reality is quieter, heavier. Venus is not gentle. Its surface pressure is over 90 times that of Earth's, the equivalent of being under a kilometer of ocean. Temperatures hover near 465 degrees Celsius, hot enough to melt lead. The atmosphere is mostly carbon dioxide, with clouds of sulfuric acid drifting high above. There is no blue sky, no wind in the familiar sense, only density, only heat, and yet it turns, slowly. One day on Venus, the time it takes to rotate once, lasts 243 Earth days, but its year is shorter, 225 Earth days, and stranger still, it rotates in the opposite direction. On Venus, the sun would appear to rise in the west and set in the east, if one could see the sky at all. But the clouds block that view completely. The thick layers of gas create a permanent twilight on the surface. Light does penetrate, but it is muted, orange, filtered. There is no shadow, only ambient glow, and the clouds never part. They encircle the planet with convective churn, shaped by winds that move far faster than the planet itself. At high altitudes, the atmosphere rotates every 4 Earth days, a phenomenon called superrotation. The contrast between the slow surface and the fast upper winds creates a planet divided by layers of time. Sound would carry well here. The density of the air would allow low-frequency sounds to travel farther. But there is nothing to speak. No rivers, no forests, no storms in the form we know. Just chemical processes, lightning in the upper atmosphere, and the slow grind of volcanic plains below. The surface is volcanic, not recently active as far as we know, but sculpted by lava flows, ridges, and broad highlands. Mountains rise through the haze. Maxwell Montes is the tallest, higher than Everest, but unseen by human eyes. Radar mapping by missions like Magellan revealed the terrain in echo and shadow, not in color. There are impact craters too, but fewer than on Mercury or the Moon. The atmosphere shields Venus from many small meteoroids, and the surface seems young, geologically speaking. Perhaps it was resurfaced in a massive event hundreds of millions of years ago, when lava erased the older crust. Or perhaps it changes slowly, invisibly, under that dense atmosphere. We are not certain. Landers sent to Venus have not lasted long. The Soviet Venera probe survived for minutes, at most a couple of hours, before succumbing to the pressure and heat. Images sent from the surface show flat rocks, dusty plains, a sepia-toned world distorted by thick optics and atmosphere. The silence is not peace, it is pressure. Venus does not speak in voices, it speaks in resistance. Everything about it pushes back, against instruments, expectations, understanding. Yet it is Earth's twin in size and composition, a near match in diameter, mass, and gravity. Once, they may have been more alike. Venus could have had water, clouds of a different kind, temperatures low enough for oceans. But something changed. Perhaps a runaway greenhouse effect, where early heat caused water to evaporate, and water vapor, a potent greenhouse gas, trapped more heat, accelerating the cycle. Over time, oceans boiled away, hydrogen escaped to space, and carbon dioxide took over. Or perhaps Venus never had oceans at all, and its path diverged from Earth's at the beginning. In either case, Venus is a mirror, not in light, but in possibility. It shows what a rocky planet can become when balance is lost. It is a study in scale, in atmospheric physics, in planetary destiny. It is also still. Tectonic activity, if present, is minor. There are no plate boundaries like Earth's, no continents moving, just vast volcanic plains, domes, coronae, circular structures formed by upwelling magma that did not erupt but deformed the crust. These features lie quiet now, or so we believe, but without clear monitoring, we cannot say for certain. Venus remains hidden, not by distance but by its own structure. Orbiting probes like ESA's Venus Express and Japan's Akatsuki observe from above, tracking weather patterns, measuring chemical composition. But the surface remains elusive. What little we know, we've learned by listening to echoes, by sending signals through the clouds and waiting for return. This delay, this indirectness, adds to the dreamlike quality of Venus. It is close, the closest planet to Earth, yet feels unreachable. In the sky, it shines steadily, not twinkling like stars because its light reflects from a broad disk rather than a point. It is unmistakable when visible, brighter than anything but the moon and sun. Yet it reveals almost nothing. It is the most observed and least understood of the inner planets. As we pass above its cloud tops, moving through the upper atmosphere, we find layers of complexity. There is a region, about 50 kilometers up, where temperatures and pressures are more Earth-like. Some have speculated, only theoretically, about floating probes or aerostats existing there for long durations. But that is a different kind of story, one of engineering and future missions, not this one. Tonight we drift, we observe. Venus, in its bright silence, turns slowly below. The clouds, shaped by forces deeper than weather, swirl and shift in massive patterns, unbroken. Lightning flashes occasionally in the distance, illuminating nothing. The planet remains as it is, bright in reflection, dense in composition, and quiet in every other way. The more we learn about Venus, the more questions remain. It is not a mystery in the romantic sense, not a place hiding secrets by intention, but one shaped by layers that resist inquiry. The thickness of its clouds, the intensity of its pressure, the sameness of its terrain, all these factors obscure detail. But there is structure within the haze. The atmosphere is not uniform. It changes with altitude, with latitude, with time. Near the poles, swirling vortexes spin, double-eyed cyclones that churn endlessly, slowly shifting their position and shape. These polar features are not storms in the sense of Earth's weather systems. They are atmospheric structures, persistent, massive, formed by the complex balance of thermal gradients and planetary rotation. From orbit, they resemble great spirals of cloud, textured like fluid, bordered by temperature bands. There is motion here, but no noise, no airliners, no birds, no surface winds strong enough to sculpt. The only motion is chemical. The slow reactions of gases, the occasional lightning discharge, the upward lift of volcanic gases that may still, sometimes, rise unnoticed. Venus is active, but in a way that does not invite. Its light, reflected from its cloud tops, hides the dense stillness beneath. That stillness is not peace. It is a form of totality, a saturation of condition. No single element dominates Venus. It is not only hot, or only bright, or only acidic. It is all of these continuously, without break. A landscape in stasis, not because it does not move, but because it moves uniformly, without punctuation. Venus has been called Earth's twin, but it is more a sibling in name than in fate. The comparison exists because of size and mass, but the differences are more telling. Venus has no magnetic field. Its rotation is retrograde and slow. Its atmospheric composition is wholly unbreathable. Its surface is unreachable without destruction. And yet, when we study Earth's climate, when we model its potential futures, we often look to Venus, not as a prediction, but as a boundary, a reminder of thresholds. What happens when a planet fails to regulate, when heat exceeds capacity, when balance is broken? Venus is not an allegory, it is a planet, ancient, massive, complex, but it offers contrast, and contrast sharpens perception. It shows us that proximity to the Sun is not destiny, but context. That planetary outcomes are not predetermined, but the product of feedbacks and chance and history. The clouds that reflect so much light, making Venus shine even during twilight hours on Earth, also trap immense amounts of heat. The albedo deceives. Beneath the brightness lies opacity. Nothing escapes easily, not light, not probes, not energy. Venus is also slow to change. Its atmospheric cycles span centuries. Its surface, absent tectonic plates, adjusts over millions of years. If there are volcanoes, they may erupt once in an epoch. If the clouds shift, they do so not in weather patterns, but in planetary breathing, deep, layered, almost geologic in timescale. The idea of time on Venus is hard to pin down. One could say it is fast. In the upper atmosphere, winds circle the planet in days. Or that it is slow, a day longer than its year, a surface that sees little change over eons. Both are true. Time here does not flow evenly. It pools, it disperses, it becomes circular, like the patterns of clouds above the poles. And so, as we move away from Venus, we carry this slowness with us. The brightness fades only gradually. Venus remains visible even when far, casting its reflected light back toward us long after we have left. In the night sky of deep space, it shines not with warmth, but with memory, a point of resistance, a world where light enters but does not escape. Between Venus and the next planet lies Earth. The distance is not far in astronomical terms, yet what we approach is profoundly different. Earth, like Venus, has clouds. It has volcanic history, atmospheric layers, chemical complexity, but it also has oceans, life, variability, transparency. It does not resist observation in the same way. It shows itself, imperfectly, but willingly. Before we arrive, we pass through the region of space where Earth and Venus trade places in their orbit, roughly every 584 days. This synodic period marks their closest approaches, and during these windows, Earth-based instruments capture rare glimpses of Venus's deeper cloud structures using radar or ultraviolet filters. It is a reminder that even the most concealed planets can be touched, lightly, with patience and care. The next stop, Earth, may seem familiar, but seen from space it becomes something else, a marble of water and motion, a contrast to Mercury's stillness, to Venus's opacity. Earth is dynamic, not because it moves more, but because we are part of its motion. But for now, Venus continues to turn slowly behind us, its clouds closing over the path we traced, its light reaching out long after we've gone. It does not follow, it does not linger. It remains in place, bright, heavy, silent. From space, Earth does not look inhabited. It looks alive, but not necessarily occupied. Its colors shift, deep blues, scattered whites, textured greens and browns, a surface in constant motion, shaped not by impact, but by cycle. Clouds spiral across hemispheres. Ocean currents reflect and absorb sunlight. Ice caps brighten or fade depending on season, but there are no obvious signs of civilization from orbit. No cities, no movement, only patterns. And in this, Earth resembles no other planet. It is not silent. It breathes. The atmosphere, a blend of nitrogen, oxygen, trace gases, and water vapor, wraps the planet in a dynamic shell. It shields from radiation, distributes heat, and moves in global patterns that drive weather, storms, and calm. Unlike Venus, Earth's clouds form and dissolve quickly, responding to ocean temperatures, land masses, and solar input. The weather changes by the hour, the season, the latitude. Yet despite this variability, a balance is maintained. A self-regulating system, not perfect, but resilient. Earth is not the largest rocky planet, not the closest to the sun, not the fastest, but it is the only one with liquid water at the surface. In vast continuous bodies, oceans cover over 70% of the planet. These oceans are not static. They transport heat from the equator toward the poles. They store carbon. They shape weather. And beneath their surface, a different kind of stability exists. One that changes slowly over centuries and millennia. Life began here in water. And though this story avoids the biological, it is impossible to separate Earth from life, not because life is dramatic, but because it alters everything else. Oxygen in the atmosphere is not a given. It is a result. The color of the sky, the erosion of mountains, the presence of soil, all are shaped, at least in part, by biology. The crust of Earth is divided, not evenly, but distinctly, into tectonic plates. These plates move, slowly but constantly. They create mountains, open oceanic trenches, trigger quakes. This movement refreshes the surface, recycles materials, and connects deep interior heat to surface processes. No other planet we've seen has this ongoing tectonic activity. It is not obvious from space, but its effects are everywhere. And so Earth is not a preserved record like Mercury, nor a buried one like Venus. It is a rewriting planet, one where the past is layered, sometimes erased, often transformed. Mountains rise and are worn down. Rivers cut through plains, then shift. Deserts grow and retreat. And ice, when present, sculpts as it melts. The poles hold immense reservoirs of water, locked in glacial structures that grow and shrink with orbital cycles. Earth's tilt, approximately 23.5 degrees, gives rise to seasons. This tilt, stable due to the presence of the moon, ensures a rhythm to temperature and light that has shaped surface conditions for millions of years. Without the moon, the tilt might vary chaotically, but with it, Earth remains in a slow, predictable wobble, a cycle of 26,000 years known as axial precession. The moon, though not the focus of this chapter, is essential. It regulates tides, slows Earth's rotation over long time spans, and offers a reference point for orientation and time. It is the largest moon relative to its planet among the rocky worlds, and its influence is constant. But Earth, even without the moon, would still be remarkable. Its magnetic field, generated by a liquid iron core, creates a protective bubble, the magnetosphere, that shields the atmosphere from solar wind. This field traps charged particles, forming radiation belts, and creates auroras when those particles interact with atmospheric gases near the poles. It is dynamic, flipping polarity every several 100,000 years, but generally stable. Beneath the surface, the mantle circulates. Heat from the core drives slow convection, influencing plate tectonics, volcanic activity, and the creation of new crust. The crust itself varies in thickness, thin beneath oceans, thick beneath continents. It is the thinnest layer, yet the one we inhabit, observe, and measure most easily. From high above, however, these details are invisible. Earth rotates once every 24 hours, creating the cycle of day and night. It orbits the Sun every 365.25 days, prompting leap years to keep calendars aligned. These numbers feel precise, but they drift slightly. Tidal forces slow the rotation. The orbit shifts over millennia. The constants are not absolute. They are approximations, anchored in time but not immune to change. From a distance, the planet glows softly. Its atmosphere scatters blue light, giving it its familiar color, but clouds reflect white, and land masses vary. Storm systems mark it as active. Hurricanes, cyclones, jet streams. These are signs of energy distribution, not disorder. There is no perfect stillness here, but there is equilibrium. When spacecraft leave Earth and look back, the planet appears delicate, not because it is small, but because it is layered. Its systems are interdependent. Water evaporates, rises, cools, condenses, and falls. Carbon moves between rock, ocean, air, and organism. Energy from the sun is absorbed, reflected, emitted. These cycles are not fast. They unfold over hours, years, or millennia. But they define Earth's character, dynamic balance. And balance here is not silence. It is movement within limits. Boundaries that shift but do not vanish. Earth is not static, but it is stable, within ranges that allow complexity to persist. This complexity is sometimes mistaken for noise, but it is coherence, a layered harmony of systems. Seen from space, Earth does not announce itself. It turns, it reflects, it holds atmosphere, it carries water, and within that, a possibility that is rare, perhaps unique. But tonight, we observe it as one planet among many. Not superior, not central, just present. Intricate, balanced, and turning slowly beneath scattered light. From above the atmosphere, Earth has no borders, no names written across land masses, no cities glowing in daylight. Its surface is continuous, textured by mountain ranges, deserts, forests, and oceans, but uninterrupted by division. At night, lights begin to appear. Soft grids and clusters outlining coastlines, rivers, and continental shelves. These lights mark human presence, but they do not alter the rotation of clouds, the shape of storms, the spread of ice. The planet moves with or without attention. And its systems, ocean currents, atmospheric cells, tectonic drift, continue regardless of interpretation. Observation changes nothing about their path, but it does alter our relationship to them. From this distance, the planet becomes quiet, not silent in sound, but quiet in demand. It does not insist. It turns, it warms, it cools. And for the first time in this journey, we witness a planet not only shaped by natural forces, but actively shaping them in return, through feedback, through adaptation, through the invisible influence of life. Photosynthesis shifts atmospheric gases. Microbes alter soil chemistry. Coral structures shape reefs. Trees affect rainfall. The boundary between geology and biology blurs, and in that blur, complexity deepens. Yet none of it is obvious from orbit. The signs of life are indirect. The presence of oxygen, the imbalance of gases, the reflectivity of chlorophyll. These are clues, not declarations. Earth remains modest in presentation. Its uniqueness is not in spectacle, but in subtlety. The only world, so far, where liquid water, an active atmosphere, and a magnetic field coexist in stable feedback, where chemical cycles move not only through rock and air, but through organisms. This integration of systems means Earth is not only dynamic, but sensitive. A change in one layer influences others. Volcanic eruptions alter climate. Ocean temperatures shift weather patterns. Ice cover affects sea levels and albedo. There is no isolation of events. Everything is connected, Not instantly, not predictably, but deeply. This sensitivity gives Earth resilience, but also vulnerability. Its balance is strong, but not unbreakable. Yet this too is not a warning, only a description. The planet has endured asteroid impacts, glacial epochs, magnetic reversals. It has seen continents merge and separate. Life has nearly vanished and regrown. And still, the pattern continues. Earth's orbit is not a perfect circle. It is an ellipse, mild but measurable. Its distance from the Sun varies slightly over the year, contributing to seasonal differences in energy. These changes, along with tilt and wobble, form cycles known as Milankovitch cycles. Long-term shifts that influence climate patterns over tens and hundreds of thousands of years. In this way, even Earth's orbit participates in its climate. Its position in space shapes conditions on the surface, not through abrupt change, but through quiet persistence. Time here is layered. A second is defined by atomic resonance, a day by rotation, a year by revolution. But these units sit atop deeper rhythms: glacial advance, sea level rise, species migration. The human sense of time fits awkwardly within these scales. From space, Earth's motion is smooth. From the surface, it feels fragmented. But neither view is wrong. They are simply different positions within the same system. The Moon, orbiting at a distance of roughly 384,000 kilometers, reflects light back toward Earth and stabilizes its axial tilt. Its gravitational pull causes tides in the oceans, which in turn affect heat distribution, nutrient cycles, even certain biological rhythms. The Moon is not distant in effect, only in position. And soon, as we continue outward, it will become our next focus. For now, Earth fills much of the view. Its disk occupies the center of vision. As the spacecraft drifts farther, or as the thought experiment expands, that disk begins to shrink. Weather systems become patterns. Coastlines merge into continents. And eventually, Earth becomes a sphere. A full planet, not a landscape. Its motion becomes apparent. Slow rotation, cloud shadows moving, the glint of sunlight on water. No other planet shows such reflectivity. Venus is bright, but due to clouds. Mercury and Mars reflect rock. Earth shines because of water, because of sky, because of balance. And in that reflection, it reveals nothing about its complexity, only its presence. As we pull away, we pass through regions filled with satellites, debris, spent rocket stages. Signs of a species that reached outward, briefly, persistently, but not yet far. These artifacts orbit Earth at various altitudes, some in low Earth orbit, some in geostationary paths, moving at speeds that defy ground-based intuition. They are silent, mostly. Instruments, transmitters, husks. They form a halo around Earth. Not natural, not permanent, but real. Beyond them, the influence of Earth fades. Gravity weakens, though it never fully ends. Magnetic protection becomes thinner. Radiation increases. The boundary between Earth's domain and cislunar space is not a wall, but a gradient, a region of transition. And in that space, the Moon waits. It does not glow by itself. It reflects Earth's light. Its surface is ancient, unprotected by atmosphere marked by impacts frozen in place. But it is next. Earth behind us now continues on, turning, balancing, quietly present in the solar rhythm, not the center, not the exception, only the setting from which we briefly looked outward. Mars is not red in the way fire is red. It is the red of rust, of oxidized iron, of ancient dust suspended in a thin sky. The color is diffuse, not glowing, but ever-present, covering rocks, cliffs, plains, a fine powder that coats everything, born from eons of chemical exposure. carried by wind across valleys and craters. It is not uniform, but it is consistent. From space, Mars appears desolate, but not in a dramatic way. It is empty in the way of long abandoned places, shaped, eroded, exposed. Its silence is not the result of isolation, but of endurance. A thin atmosphere still exists, composed mostly of carbon dioxide, with traces of nitrogen and argon. It presses down at less than 1% of Earth's surface pressure. Too little to breathe, too little to carry much heat, but just enough to move. And it moves. Dust is lifted. Skies change. In some seasons, entire hemispheres become veiled in storm. Winds rise and settle without sound. There is weather here, not in the familiar patterns of Earth, but in long, slow drifts and global pulses. Mars rotates in just over 24.6 hours. Its days, or sols, are close to Earth's in length. Its axial tilt is also similar, around 25 degrees, which gives rise to seasons. But they are not the same. The Martian year is nearly twice as long. Seasons last for months. Temperatures shift, but rarely reach warmth. Even at midday near the equator, surface temperatures struggle to climb above freezing. At night, they plummet. Water, when present, is locked in ice. Near the poles, vast deposits of frozen carbon dioxide and water accumulate, growing in winter, retreating in summer. These polar caps are layered, patterned with bands that reflect past climate cycles. A Martian memory etched in frost. Mars has no global magnetic field. As a result, solar radiation reaches the surface unimpeded, and atmospheric particles are slowly stripped away by the solar wind. The loss is gradual, but significant. Over billions of years, it reshaped the planet. Once, perhaps, Mars held more air, more warmth, liquid water flowing freely. The surface suggests this. Dried riverbeds, delta formations, sedimentary layers. Not illusions, not interpretations. Structures, patterns, leftovers of motion. Ancient lakes, now empty, show signs of evaporation. Craters hold layered deposits. In some regions, mineral compositions point to long-term interaction with water. Clays, sulfates, carbonates. These are not scattered anomalies. They are widespread, consistent. They tell a quiet story. That Mars was once different, not Earth-like, but more dynamic, more fluid. And then, slowly, it changed. The core cooled, the field faded, the atmosphere thinned. Water withdrew, but traces remained. Mars did not erase its history. It preserved it in stone. Olympus Mons, the tallest volcano in the solar system, rises over 21 kilometers above the plains. Its flanks are broad, sloping gently over hundreds of kilometers, evidence of lava flows that spread slowly over time. There are no tectonic plates on Mars. Volcanic regions do not shift. Instead, the crust remains fixed, allowing massive edifices to form over long durations. To the east, Valles Marineris cuts across the planet, a canyon system over 4,000 kilometers long, 200 kilometers wide in places, and up to 7 kilometers deep. It is not a river valley. It is a fracture widened by erosion and collapse, shaped by tectonic stress and time. Its walls reveal layers of Martian history, sedimentary records, volcanic layers, dust. It is not carved, but opened. A wound in stone. The surface is dotted with impact craters of all sizes, some ancient and eroded, others sharp and recent. Unlike Earth, where wind and water erase such features, Mars keeps them. They serve as time markers. A fresh crater may be only years old. An older one, softened by dust, might date back billions. These craters are not random. Their distribution, density, and overlap help estimate the age of surfaces. In this way, Mars offers not just a landscape, but a calendar. Rovers and orbiters have explored it for decades. Each mission adds detail: temperature profiles, mineral maps, atmospheric measurements. None of them find motion in the way we define life, but all find evidence of past transitions. Mars is not static, it is simply slow. Its activity is measured in erosion rates, in dust deposition, in seasonal frost patterns. Avalanches still occur on steep slopes. Ice sublimes and redeposits. Dust devils, vertical columns of rotating air, sweep across the plains, briefly lifting sediment, leaving dark tracks that fade over days or weeks. These are the movements of a world without urgency. And in that slowness, Mars reveals its presence. Its two moons, Phobos and Deimos, are irregular, small, likely captured asteroids. They orbit rapidly, with Phobos completing a revolution in under 8 hours. From the surface of Mars, Phobos rises in the west and sets in the east. A backwards motion, fast and low. Deimos moves slowly across the sky, almost star-like in appearance. These moons offer little in terms of tidal influence, but they are companions. Not stabilizing forces, but markers of orbital complexity. As we descend into the thin Martian air, or what remains of it, the transition is gentle. There is no dramatic entry, no roaring turbulence, only thinning density and shifting composition. The surface comes into view quietly. Reddish terrain, wind-smoothed, cratered, rising and falling in subtle patterns. Dunes ripple across basins. Rock outcrops pierce the dust. And occasionally, in the shadow of cliffs or beneath frost, ice reflects a pale glint. Mars does not welcome or resist. It endures, and in that endurance, it invites observation, not with urgency, but with patience. Mars holds time differently. On Earth, weather changes daily, coastlines shift over centuries, forests grow and recede. But on Mars, centuries pass with little surface alteration. The dust is moved, yes. Frosts come and go, but the shape of the land remains. Not because it is inert, but because its changes occur across scales that extend beyond human memory. Even its storms, though vast, are slow. Sometimes they cover the entire planet, not with thunder or rain, but with fine particles of oxidized iron lifted into the air. These global dust storms can last for weeks or months, muting the light, lowering temperatures, reducing visibility to meters. And then, without signal, they fade. The sky clears, the dust settles, and the landscape returns, the same, yet slightly altered, subtly retextured. The Martian atmosphere, though thin, supports this rhythm. It breathes in frost at the poles each winter, exhaling it again with the return of spring sunlight. These carbon dioxide cycles affect pressure, wind patterns, even the tilt of the planet over long periods. It is not a weather system in the Earth sense. It is a global pulse, driven by insolation, by season, by orbital position. Mars is not warm, but it is not absolutely cold either. At the equator, during midsummer, surface temperatures can reach 20 degrees, but only briefly. Just above the ground they fall quickly, and at night they plummet. The absence of atmosphere means heat does not stay. Radiation escapes directly into space. Frost can form even in places warmed by midday sun. This stark fluctuation gives Mars a distinct rhythm. Heat without retention, energy without insulation. Still, within this narrow band of conditions, complex interactions take place. Permafrost lies just beneath the surface in many regions. Salty brines, stable at lower temperatures, may exist in small quantities. Some dark streaks observed on slopes, called recurring slope lineae, have been interpreted as potential signs of seasonal water flow, though the evidence remains debated. Whether or not liquid water exists today, the memory of it remains strong. Every valley network, every delta fan, every clay-rich basin is a reminder, not just of presence, but of motion. Water once moved here, slowly, heavily, shaping stone, altering chemistry, perhaps pooling in basins that held it for thousands of years. Mars preserves these signs. It does not wash them away. Even impact craters bear evidence of interaction with water. Ejecta patterns suggest mud flows. Some craters contain layered sediments, deposited in still lakes or ephemeral seas. The rocks remember, even when the sky forgets. In the modern era, Mars is a host to many machines, orbiters, landers, rovers. Each explores with deliberate slowness, measuring composition, capturing images, recording atmospheric data. The rovers, from Pathfinder to Spirit and Opportunity, from Curiosity to Perseverance, move across the surface at human walking speed or slower, pausing often to study rocks, dust, radiation. They are not in a hurry. Their mission is time. Their path is patience. And through them we see a world that feels familiar in shape. Hills, plains, valleys, yet alien in response. Nothing moves unless pushed. Nothing changes without cause. The wind may whisper across the sand, but it does not speak. There are no rustling trees, no flowing streams, no bird song. Only the occasional shift of dust, the faint motion of shadows, the ticking of instruments. And overhead, a sky that changes colour with the angle of the sun. Pale orange at noon, deeper red at dusk, sometimes tinted blue at sunrise near the horizon. A different kind of blue, scattered by the fine particles of Martian air. Earthlight is not visible from the Martian surface. Earth appears as a star, bright but unremarkable. One among many, the sun, smaller and dimmer than on Earth, casts long shadows across the terrain. It rises and sets slowly, tinted by dust. Seasons come, not with blossoms or melting snow, but with subtle shifts in light, in frost, in wind direction. These seasons matter for dust accumulation, for CO2 deposition, for long-term climate trends. But they do not transform the landscape visibly. They leave no immediate trace. The moons, Phobos and Deimos, cross the sky rapidly. Phobos, the closer and faster of the two, appears and disappears in under 4 hours, moving from west to east. It casts shadows, causes minor tides in the atmosphere, and is slowly spiraling inward toward Mars, destined to break apart or crash in millions of years. Deimos, more distant, moves slowly, barely changing position across a night. Neither moon stabilizes Mars's tilt. Without a large satellite, the Martian axial tilt varies more over geological timescales. This has influenced climate history. Polar ice redistributions, changes in surface erosion, glacial flow. Mars is not simply a smaller Earth. It is an experiment in what happens when certain conditions, atmosphere, magnetism, plate tectonics, are missing or diminished. It tells a version of the planetary story where motion slows, where change is frozen mid-step, where potential becomes preservation. And as we drift outward from Mars's thin grip, passing through orbits of its moons, the solar light weakens slightly. The warmth of the inner planets begins to give way to the cold structure beyond. Before us lies a region, not dominated by one object, but filled with many, irregular, scattered, ancient. The asteroid belt, a zone of remnants, of fragments that never formed a planet, shaped instead by the presence of Jupiter. But that is the next step. Mars, now behind us, continues its long orbit. Slow, elliptical, tilted slightly from the plane. A red world, not blazing, not burning, but cooling in stillness, watching, remembering, turning endlessly under the thin breath of its own sky. The asteroid belt does not resemble the crowded scenes imagined in fiction, where rocks tumble dangerously close to one another, narrowly missing as spacecraft weave between them. In reality, the belt is mostly space. The asteroids are scattered across a vast volume between the orbits of Mars and Jupiter, from about 2.1 to 3.3 astronomical units from the Sun. They orbit quietly, each in its own path, separated by millions of kilometers. To see one from another, you would need instruments or time. This region holds billions of objects, from dust-sized grains to bodies hundreds of kilometers across, but they are not evenly distributed. Their spacing follows patterns shaped by resonance with Jupiter. At certain distances, gravitational influence from the giant planet has cleared gaps, the Kirkwood gaps, where few objects persist. These orbital absences speak of time and mass, of long interaction. The belt is not a relic of a broken planet. It is a region where a planet never formed. Early in the solar system's history, the material here tried to coalesce. Collisions occurred, growth began. But the pull of Jupiter disrupted the process. The result is a field of fragments, remnants of early formation, never gathered, never finished. They range in shape, in size, in composition. Some are rocky, some metallic, some icy, some porous, others solid. Many are irregular, tumbling slowly through space. Others are nearly spherical, pulled into form by gravity. Ceres, the largest object in the belt, is over 900 kilometers in diameter, enough to qualify as a dwarf planet. It holds internal structure, water ice, perhaps even briny subsurface layers. It is not active in the way planets are, but it shows differentiation. It has a history. Vesta, another major body, is smaller but more reflective, with surface patterns indicating ancient volcanic activity. Its structure suggests a core, a mantle, a crust, like a planet in miniature. Meteorites found on Earth, known as head meteorites, are believed to originate from Vesta, ejected by impacts long ago. These fragments tell stories not through language, but through isotopes, through crystal alignment, through cooling rates frozen in mineral form. Most asteroids are smaller. Measured in kilometers or less, they rotate. Some spin rapidly, others slowly. Some are monolithic. Others are rubble piles, loosely held together by gravity and the cohesion of dust. Collisions still occur, though rarely. When they do, debris is scattered, sometimes creating asteroid families. Groups of bodies with similar orbits and compositions, born from the same impact. These families drift over time, their paths altered by sunlight. The Yarkovsky effect, a subtle force from the way heat is absorbed and re-radiated, gradually changes their orbits depending on spin, shape, and composition. In this way, light shapes motion very slowly. The entire belt contains only a fraction of Earth's mass, less than 5%. Yet its spread is immense, a cloud of slow-moving objects orbiting in ellipses slightly tilted, slightly eccentric, held loosely by the Sun, but bounded by Jupiter's influence. The temperature here is low, but not frozen. Sunlight still reaches. The average surface temperature on a typical asteroid is around -100 degrees Celsius. Ice can exist in shadows, especially on the outer edge of the belt. But heat does not fluctuate much. There is no atmosphere, no weather, only rotation, radiation, impact. Spacecraft have visited this region. Dawn orbited Vesta, then Ceres, using ion propulsion to move between orbits. The first mission to orbit 2 extraterrestrial bodies. It revealed craters, ridges, strange bright spots in Ceres' Akaita crater. likely salts from briny subsurface water exposed and sublimated over time. These spots do not shine. They reflect, but even this reflection is subdued, spread thin over a vast, cratered plain. Other missions have flown past smaller asteroids, Ida, Gaspra, Matilda, Lutetia, capturing irregular forms, jagged shadows, boulder-strewn slopes. Each object is different. Each tells a specific local story. But taken together, the belt speaks in patterns, in composition gradients, in orbital families, in population distributions. It is not static. It evolves, slowly, subtly. Collisions create fragments. Solar pressure shifts orbits. Jupiter nudges. The belt breathes in the gravitational sense. Stretched across time, responsive to distant mass. It is also a source of visitors. Some near-Earth asteroids originate here, thrown into elliptical paths by resonance or collision. Meteorites found on Earth trace their origin to this region. Messengers of the past, silent travelers that crossed millions of kilometers before meeting our atmosphere. They vaporized on entry or landed intact, preserving chemistry from before Earth had oceans. In this way, the asteroid belt connects past and present. It is not dramatic, but it is fundamental. A record of what almost happened, a planet that might have been, and of what still might. Future resources, future exploration, future dwellings in hollowed rock or orbiting stations. But tonight, it is only a belt of stone, quiet, spinning, holding position under faint light, not clustered, not crowded, just patient, turning with the sun, around the sun, along orbits defined billions of years ago. Each object alone, yet part of a whole. As we continue outward, the belt begins to thin. There is no clear boundary, no final asteroid to mark the edge. Objects become more widely spaced. Their orbits still intersect, still evolve, but interactions grow less frequent. Collisions that once shaped families become improbable. The belt fades, not in content, but in coherence. It gives way to a quiet zone between systems, a transition space before the dominance of Jupiter begins. Behind us, the inner planets fall into alignment. Mercury, small and scorched. Venus, bright and veiled. Earth, blue and moving. Mars, red and remembering. The moon remains tethered to Earth's pull. The belt, though vast, is now behind. The journey ahead leads to mass. Not the mass of a scattered field, but of singular gravity. Jupiter waits, still distant, but already shaping the space around it. The influence of Jupiter extends far beyond its physical size. Its mass is more than twice that of all other planets combined. It bends orbits, captures moons, deflects comets. It has been called the solar system's vacuum cleaner, the great protector, the planet that reshaped early formation. But here, still near the outer edges of the belt, we can observe how that influence manifests slowly. Orbital resonances, specific ratios of motion, carve gaps in the asteroid population. The 3.1 resonance, the 5.2, the 7.3, all regions where Jupiter's repeated tug pulls objects out of stable paths. Over time, these tugs become displacements, then ejections. Objects fall inward toward the Sun, or outward toward the Kuiper belt. Some become comets, others fragment. The belt, then, is not static. It is shaped continuously by memory and motion. Memory of the solar system's formation, motion under the weight of planetary gravity. Jupiter's presence halted planet formation here. Its gravity stirred the primordial disk, increased collision velocities, prevented accretion. The result is a region of remnants, fragments of potential, but not failure. The belt plays its own role. It is a boundary, a buffer, a source of insight. Every stone carries information. Every orbit reflects a balance of force. Spacecraft continue to study it, occasionally visiting new targets, measuring albedo, mapping surface composition with infrared and neutron detectors. Yet most of what we know comes from distance, from spectral data, from trajectory calculations, from the impacts these objects make when they fall to Earth. These are quiet discoveries, no signals, no headlines, just light, shifted and reflected, interpreted over time. The objects here do not shine, they do not emit. They absorb, they reflect, they persist. Their surfaces are dark, some blacker than coal, others slightly brighter. They are irregular, porous, shaped by time and collision. Their histories are not written in erosion or weather, but in impact scars and spin states. Some tumble chaotically, others rotate in rhythm. Their orbits are predictable, but their orientations are not, and yet they remain. Each object obeys the same rules: gravity, inertia, reflection, rotation. These rules apply equally to the smallest rock and the largest planet. The difference is only scale. At the belt's outer boundary, sunlight weakens. The temperature drops further. Here, ice begins to survive more easily in shade, under dust. Some objects may hold frozen volatiles in interior layers, protected from sublimation. These are not comets, not yet, but they are close. If perturbed, they might fall inward, heat, change. For now, they remain silent, dormant, balanced. The belt gives us a lesson in possibility, that planets are not inevitable, that not every orbit leads to accumulation, that sometimes structure emerges in fragments, and that fragments too can persist. Beyond this region, the sun becomes smaller, though still bright. The stars begin to assert their presence. Jupiter approaches. Its reflected light increases. Its gravitational grip becomes dominant. The transition is not marked by an event. There is no gate, no signal, only a shift in behavior. The belt stops tugging. Jupiter starts pulling. The space between is not empty, but it is quiet. We move through it now, slowly, without urgency. Behind us, the inner system rotates, faster, denser, warmer. Ahead, the outer system opens, colder, slower, larger. In this shift, the nature of the solar system changes. Not its structure, but its mood. From rocky solidity to gaseous scale. From planetary surfaces to deep, swirling atmospheres. From light to shadow. But the asteroids remain, circling, not ending. Their paths continue. Their presence endures. Like distant bells in orbital fog. Like thoughts that never finish. Like pieces that never formed a whole, but never needed to. Jupiter is not a surface. It is a presence. A sphere of atmosphere without a solid boundary, made of gas compressed by mass into states unfamiliar to terrestrial experience. From afar, it is unmistakable. Striped, spinning, immense. The bands are clouds, arranged by latitude, driven by wind, shaped by pressure gradients. The planet rotates once every 10 hours, the fastest spin in the solar system, causing its equator to bulge slightly, flattening its poles. This rapid motion drives jet streams, eastward and westward winds stacked in belts and zones, each flowing in the opposite direction of the one beside it. There are no continents here, no oceans in the traditional sense, but there is structure, order, and chaos within it. The clouds are composed mostly of ammonia crystals, layered over deeper bands of ammonium hydrosulfide and water vapor. These layers reflect sunlight, but they also absorb and re-emit infrared heat from within. Underneath, pressure increases rapidly. Gases become supercritical fluids, neither gas nor liquid, behaving in ways that are modeled more than measured. The core, if it exists as a distinct object, may be rocky, or it may be a diffuse cloud of heavy elements. We do not know. Instruments orbiting Jupiter, such as Juno, attempt to map its internal structure through gravity anomalies, magnetic field measurements, and microwave emissions. But certainty remains distant. What is known is that Jupiter is not only large, it is massive, over 300 times the mass of Earth. Its gravity shapes the orbits of nearby asteroids, captures comets, holds dozens of moons. Some objects orbit within its radiation belts. Others trace looping paths far from the equator, inclined and eccentric. This complexity forms a miniature solar system, a planet with its own family of bodies, each with its own motion and rhythm. From orbit, the great red spot stands out, a persistent anticyclone, larger than Earth, spinning for centuries. Its color varies, its borders shift, but it remains, not fixed in position, but consistent in latitude. It is not the only storm. Other vortices spin across Jupiter's surface. Smaller ovals, elongated disturbances, transient waves. The planet is fluid, not only in substance, but in behavior. Storms form, merge, decay. Jet streams accelerate or weaken. Cloud layers rise and sink. Yet the underlying patterns remain. Jupiter's magnetic field is immense, generated by motion within layers of metallic hydrogen, a phase of matter created under extreme pressure. It extends millions of kilometers into space, forming a magnetosphere that dwarfs the Sun itself in volume. Within this field, charged particles are trapped, forming intense radiation belts far more dangerous than Earth's Van Allen belts. These zones can disable unshielded electronics in minutes. The field also interacts with Jupiter's moons, especially Io, where electromagnetic flux induces volcanic activity, and where the moon's own movement generates electric currents along magnetic field lines. The result is a glowing aurora, not at the poles alone, but in persistent rings where particles funnel along field paths. These auroras are visible in ultraviolet, shifting, flaring, responding to solar wind. They are not quiet, but they are continuous. They mark the boundary between planetary and interplanetary space. Approaching Jupiter, the temperature drops. The light fades, but the planet itself emits heat. Residual energy from formation, compressed by gravity, radiated slowly over time. Jupiter shines in infrared, not brightly, but steadily. A reminder that even without fusion, mass itself can glow. This heat affects its atmosphere, drives internal convection, fuels storms. It also affects its moons. The Galilean satellites, Io, Europa, Ganymede, and Callisto, each tell a different story. They are not fragments, they are worlds, and they orbit in resonance, locked into ratios that maintain orbital stability and tidal stress. Io is closest, volcanic, sulfur-covered, internally heated by tidal forces. It erupts constantly, its lava fountains reaching high into a nearly non-existent sky. These eruptions replenish a thin atmosphere, feed a torus of plasma around Jupiter, and paint the surface in yellows and reds. Europa follows, smoother, colder, covered in ice. Cracks line its shell. Beneath that shell, all evidence suggests a subsurface ocean, kept liquid by heat from tidal flexing. This ocean may contain more water than all of Earth's combined. Ganymede is next, the largest moon in the solar system, bigger than Mercury, with its own magnetic field, ice crust, and possible internal ocean. Its surface is a patchwork of bright and dark regions, shaped by tectonic activity and ancient impacts. Callisto, farthest out, is quieter, heavily cratered, undifferentiated, and ancient, a surface that may not have changed for billions of years. All 4 moons are visible in small telescopes from Earth, first seen by Galileo in 1610. But from here, they are not points of light. They are worlds in orbit, trailing and leading, crossing in shadow, casting eclipses on Jupiter's cloud tops. The system is dynamic. Eclipses occur regularly, transits, occultations. The geometry is rich, complex, calm. Jupiter's gravity dominates, but its family moves with precision. A slow ballet in gas and stone. And through it all, the planet spins, vast, banded, humming with radiation, cloaked in cloud, rooted in pressure. It has no ground, but it has weight and presence. The Galilean moons orbit in resonance, a quiet numerical harmony. For every 4 orbits of Io, Europa completes 2, and Ganymede completes 1. This 4:2.1 resonance is not coincidence, but the result of long gravitational interaction. It maintains orbital spacing, regulates energy transfer, and sustains tidal heating. It keeps their paths stable, yet active. Especially for Io and Europa, this interaction is not just mechanical. It shapes geology. It drives interior motion. Io, closest to Jupiter, is a surface of constant upheaval. Its yellow plains and black calderas mark volcanic activity unceasing. Lava lakes churn. Plumes rise hundreds of kilometers. The energy does not come from internal decay, as on Earth, but from motion, orbital flexing under Jupiter's pull. It stretches and compresses, friction building heat. No other world in the solar system is so volcanically alive. Yet Io has no water. Its activity is dry, driven by sulfur and silicates. It is both ancient and new. Craters are rare, resurfaced quickly by eruptions. And above it, the plasma torus glows, a ring of charged particles ejected by Io's volcanoes, trapped in Jupiter's field. Europa, farther out, is colder. Its surface is ice, smooth in places, fractured in others. Crisscrossing ridges, double lines, chaotic terrains where crust has broken and refrozen. Underneath, evidence points to an ocean. Salt water, deep and global, warmed by the same tidal forces that tear Io open. The ice acts as insulation, cracks as windows. Occasionally, plumes have been detected rising from Europa's surface, likely water vapor, ejected through fractures. These outbursts offer a way to study the ocean indirectly by passing through the spray, sampling particles. Missions are planned. Europa does not erupt visibly like Io. It does not shine in color, but it holds potential for chemistry, for cycles, for depth. Ganymede is larger than both. It shows signs of internal differentiation, a rocky core, a subsurface ocean, a magnetic field. It is the only moon with one, generated by fluid motion within like Earth's, though weaker. Its surface bears grooves and ridges, tectonic in origin. The bright regions suggest stretching, the dark ones older crust. There is no clear symmetry. Ganymede is a layered world, a record not of one process, but of many. Ice, rock, magnetism, inertia. Callisto, in contrast, is quieter, no resonance with the others. Its surface is ancient, saturated with craters. It shows little internal evolution. Perhaps its core never melted. Perhaps it formed late, after the heat of formation had passed. But even here, in silence, there is information. Stability can be as revealing as motion. Jupiter's lesser moons, dozens more, form clusters, irregular paths, inclined orbits. Many are thought to be captured asteroids or fragments of larger bodies broken by impact. They circle the planet distantly, loosely held. Not part of the inner ballet, but still bound. As we move outward, past the orbit of Callisto, the light from Jupiter begins to soften. The radiation belts weaken. The sky grows darker, colder. The planet shrinks behind us, though its presence lingers in trajectory, in gravity, in rhythm. It takes nearly 12 Earth years for Jupiter to orbit the Sun once. Its year defines the timing of resonances, the spacing of asteroids, the motion of comets. It is a regulator, not by intention, but by mass. Its stability has shaped the solar system's long-term balance. And now, as we leave its sphere of dominance, we approach the next. Saturn. Between them lies space, not empty but sparse, occasionally crossed by centaurs, icy bodies in unstable orbits, and by dust, and by the faint whispers of solar wind. There is no event that marks the exit from Jupiter's realm. Only distance. The moons thin out. The light flattens. The path turns slowly toward a planet defined not just by mass or motion, but by pattern. Saturn is not far. But before we reach it, one final glance at Jupiter. A sphere of motion, wrapped in storms, encircled by moons. It has no ground, no sky in the human sense. But it has weather, pressure, rotation. And through that, it holds shape. Not a surface to land on, but a system to orbit, to observe, to measure, to think through. Its storms turn for centuries. Its bands flow endlessly. And its gravity, even when distant, still curves the paths of smaller things. Saturn is the farthest planet visible to the unaided eye, the last of the classical wanderers, a pale yellow point in Earth's night sky. But from here, from within its gravitational reach, it is not a point. It is a system, vast, patterned, layered. It rotates every 10.7 hours, drawing its clouds into bands like Jupiter, but softer, more diffused. The contrasts are less violent, the atmosphere more subdued. Hues of gold, beige, and cream flow in curves, shaped by winds that reach over 1,800 kilometers per hour near the equator. Saturn's atmosphere is composed primarily of hydrogen and helium, like Jupiter, but with subtle differences in trace elements and cloud chemistry. Ammonia crystals form the uppermost visible layers. Deeper down, water and other compounds exist, compressed under pressure beyond direct observation. There is no solid surface, no place where gas becomes ground, only increasing density, only transition. Like Jupiter, Saturn emits more energy than it receives from the Sun. Residual heat from formation, slowly escaping, drives convection, fuels banded flow, and contributes to long-term atmospheric evolution. Its shape is more flattened than Jupiter's. The equatorial diameter is significantly larger than the polar diameter, the result of rapid rotation and lower density. Saturn is the least dense planet in the solar system. If a body of water large enough existed, Saturn would float. A poetic truth, but a physical one. The most iconic feature, of course, is the rings. Thin, wide, bright, composed of ice particles, ranging from grains to boulders. They are not solid. They are not static. They are a rotating field of frozen fragments, orbiting in a plane only about 10 meters thick in some regions, but spreading over 280,000 kilometers in diameter. Each ringlet, each gap, is shaped by resonance, by moonlets, by subtle gravitational tugs. The Cassini division, the Encke gap, the F-ring. These features are not stable structures, but dynamic boundaries where motion cancels or reinforces, where particles are pushed into patterns over time. The rings are young on geological scales, perhaps 100 million years old, perhaps less. Their origin is debated, possibly the remnants of a shattered moon, a captured comet, or leftover material never accreted. Whatever their history, they represent structure born from debris, order formed by repetition. Light plays across them differently at different angles. Backlit, they glow faintly. At opposition, they shine brightly, an effect called the opposition surge, caused by the direct alignment of sunlight and observer, reducing shadows between particles. Up close, the rings are not smooth. They are clumpy, self-gravitating at microscales, constantly colliding and redistributing energy. They do not make sound, but if they did, it would not be music. It would be a granular hiss, a dense silence made of millions of interactions per second. Saturn's rings are not its only companions. It has over 80 confirmed moons, ranging in size and character. Some orbit within the rings, others far beyond. Titan is the largest, bigger than Mercury, and it is unlike any other moon in the solar system. It has an atmosphere, a thick one, composed mostly of nitrogen, with methane and other hydrocarbons. On its surface, rivers flow, lakes exist, not of water, but of methane and ethane. Hydrocarbons in liquid form stable under Titan's cold temperatures. Clouds drift, rain falls, erosion carves the land, dunes line equatorial plains. Cryovolcanoes may erupt slowly, reshaping terrain with icy slush. Titan is Earth-like in process, not in substance. Familiar forces applied to unfamiliar chemistry. Beneath its crust, a subsurface ocean of water and ammonia is thought to exist. Global, salty, and perhaps in motion. Cassini and its probe Huygens revealed much of Titan, but much remains unseen. The surface is hidden in haze. Light diffuses, softens, disappears. Shadows are faint. Distances lose contrast. It is a world of outline and gradient, not of edge and color. Other moons offer different stories. Enceladus is small, only 500 kilometers across, but active. At its south pole, a set of fissures known as tiger stripes vent water vapor, ice, and organic molecules into space. Beneath the crust, a subsurface ocean exists, warmed by tidal heating. The plumes create Saturn's E-ring, extending far beyond the moon's orbit. They also offer a path to study an alien ocean without landing, by sampling particles as they exit, as Cassini did. Tethys, Dione, Rhea, cratered, icy, older. Mimas, with a massive impact crater, often compared to a familiar fictional space station. Hyperion, rotating chaotically, shaped like a sponge. Iapetus, with one side dark as coal, the other bright as snow, marked by an equatorial ridge whose origin is unknown. Each moon holds its own equilibrium. Size, shape, orbit, surface. None is the same, and yet they orbit the same planet, drawn into its gravity, illuminated by its reflection, influenced by its field. Saturn's magnetic field is weaker than Jupiter's, but still vast. It tilts little relative to its rotation. Its interior remains a mystery, likely composed of a rocky core, metallic hydrogen, and molecular hydrogen above. But the transition is gradual. Like Jupiter, it is not a body with a surface. It is a gradient, a continuity of pressure. What makes Saturn distinct is not its depth, but its shape, not its heat, but its geometry. Its presence in the sky, when viewed from Earth, is steady, pale yellow, less bright than Jupiter, more distant. But from here, it is motion itself, spinning, ringed, encircled by companions. It does not end at its cloud tops. It does not begin at its rings. It is a system within a system. Massive, quiet, balanced. The Saturnian system is not bound by one rhythm. It is layered in time. Fast rotations, slow orbits, long-term drift. The planet spins rapidly. The rings revolve in hours. The outer moons complete circuits in days, weeks, or months. Each motion loops within another. Each orbit writes a curve inside a larger spiral. These movements do not conflict. They coexist. They harmonize by scale, not by tempo. And in this coexistence, Saturn becomes more than a planet. It is a field of activity, a structure held together by motion. The rings, though vast in diameter, are astonishingly thin. From above or below, they are clear and ordered, but seen edge-on, they nearly disappear. A knife of reflected light suspended in space. They cast shadows on Saturn's clouds near equinox, marking time in sweeping arcs. These shadows drift over the planet's upper atmosphere, tracing seasonal change. Once every 29.5 Earth years, one Saturnian year, the rings align with the Sun. Their brightness fades, their geometry becomes abstract, and then, slowly, they tilt again, regaining fullness, revealing structure. This long seasonal cycle shapes temperature gradients in the upper clouds. It defines when certain features can be observed. It modulates atmospheric chemistry, cloud patterns, and haze. Beneath the visible clouds, Saturn's weather remains partially hidden. Storms arise, including the periodic Great White Spot, a massive storm that encircles the planet roughly every Saturnian year. These events erupt, expand, fade, and leave behind chemical imprints. The rest of the time, cloud bands rotate steadily, shaped by deep flows and wave patterns. One of the strangest features sits at the North Pole, a hexagonal jet stream. First observed by Voyager and later studied by Cassini, it is a persistent six-sided vortex, 30,000 kilometers across, stable for decades. It is not static. It shifts in color, responds to seasonal light, possibly influenced by waves deep below. Yet its structure endures. It is not fully understood, but it is measured, mapped, modeled. It spins, and it remains. Saturn's magnetic field is unusual, nearly perfectly aligned with its rotation axis, defying expectations from planetary dynamo theory. It is weaker than Jupiter's, but still strong enough to trap particles, generate auroras, and affect the flow of charged dust and plasma. The auroras are not as bright as Jupiter's, but they dance around the poles, responding to solar wind, sometimes flaring during geomagnetic storms. Saturn also emits radio waves, bursts of rotational modulation used to estimate day length, although inconsistencies suggest deeper complexity in its interior. Like Jupiter, Saturn radiates more energy than it receives from the Sun. This excess may result from helium precipitation, where helium droplets fall through hydrogen layers, releasing heat. The core itself remains invisible. No probe has entered. No spacecraft has dipped below the upper atmosphere. What we know is inferred from gravity measurements, from magnetic fields, from subtle accelerations. Cassini's final orbits, the so-called grand finale, pass between the planet and its rings. These passes refined mass estimates, hinted at internal structure, measured field lines. But they left questions open. Saturn does not reveal its center easily. The moons, too, remain active subjects. Titan's atmosphere evolves under solar radiation, breaking methane into complex organics. Over time, these chemicals settle onto the surface, forming dunes, seas, and possibly prebiotic materials. Titan is not static. Its lakes rise and fall with the seasons. Methane rain reshapes terrain. The moon changes, not quickly, but perceptibly. Enceladus continues to vent from its south pole, ejecting materials that replenish Saturn's E-ring. The particles contain salts, organics, simple molecules. The plumes may originate from hydrothermal vents at the ocean floor, where rock and water meet under pressure. If so, Enceladus is not just active, it is chemically rich, a laboratory sealed in ice. And all around, dozens of other moons circle, less known, but no less real. Each contributes to the system's gravitational balance. Each shapes the rings slightly, through resonance, impact, or presence. They are parts of a whole, distributed across space, orbiting a shared center. As we pull away, Saturn remains immense, but slowly it recedes. The rings fade to a thin curve. The planet becomes a pale sphere, banded, glowing faintly in reflected light. Its moons become points. Its gravity weakens. The space ahead grows colder. The sun smaller. The darkness deeper. We cross the orbit of Titan, then of Iapetus. We pass the edge of the magnetosphere. The next region is quieter still. Fewer moons, no rings, fewer visitors, but not empty. Ahead lie Uranus and Neptune, the ice giants. Subtler, farther, colder. Their presence is not marked by brightness or mass, but by atmosphere, by tilt, by distant winds. Before we arrive, one last look back. Saturn turns, encircled by fragments, orbited by ice, illuminated by a distant star. It does not fade. It rotates, slowly. Exactly. Uranus is distant, not only in position, but in perception. It reflects pale blue-green light, the result of methane in its upper atmosphere absorbing red wavelengths. There are no bold stripes, no swirling storms easily visible. The surface, or rather, the outer cloud tops, appears calm, subdued, softly colored. But this stillness is deceptive. Uranus is unique among the planets. Its axis is tilted over 97 degrees, lying nearly sideways relative to its orbit. Its poles face the sun in turn, producing extreme seasons that last over 20 Earth years each. For part of its orbit, one hemisphere receives constant sunlight. For another, it sits in shadow. This tilt likely resulted from a massive collision early in its formation, an impact that did not destroy it, but altered its orientation permanently. The planet rotates once every 17 hours. Its atmosphere flows in bands, like other gas giants, but these bands are faint, subtle. They require enhancement to observe in detail. Winds here can reach up to 900 kilometers per hour, less than on Jupiter or Saturn, but still rapid. The atmosphere is composed mainly of hydrogen and helium, with a higher proportion of ices, water, ammonia, methane, in its interior. Beneath the clouds lies a layer of icy fluids, dense and compressed, likely forming a slushy supersonic state where water molecules break into ions. Deep below, a rocky core is assumed, but not confirmed. Uranus emits little heat, unlike Jupiter and Saturn, which radiate more energy than they receive. Uranus does not. The reason is uncertain. It may have lost internal heat during formation, or the sideways tilt may have disrupted convection. The result is a planet with faint thermal activity, low contrast, long seasons, and a strange magnetic field. The field is offset from the center and tilted at over 50 degrees from the rotational axis. It sweeps through space asymmetrically, varying in strength, producing auroras that do not align neatly with the poles. This irregularity suggests a dynamo deep within, in layers of convecting fluids. Uranus has rings, though they are dark and narrow. Composed of larger particles than Saturn's, they are not bright and were only discovered through stellar occultation. When a star's light briefly dims as the planet passes in front of it, they orbit close to the planet, shaped by small moons, each ring a trace of subtle resonance. Uranus also has at least 27 known moons, most named after characters from Shakespeare and Alexander Pope. The largest 5, Miranda, Ariel, Umbriel, Titania, and Oberon, each show different geologies. Miranda, though small, is among the most geologically varied objects in the solar system. It has cliffs 20 kilometers high, smooth plains, ridged terrain, features suggesting past tectonic activity, possibly driven by tidal forces. Ariel shows signs of resurfacing, canyons, fractures, flow features. Umbriel is darker, heavily cratered, less active. Titania and Oberon are larger, showing mixed surfaces, impact scars, ridges, and hints of internal complexity. These moons orbit in the planet's equatorial plane, which, due to the axial tilt, means they follow paths perpendicular to the solar system's general plane. From a distance, their motion is peculiar, like a wheel spinning on its edge. The Uranian system turns sideways through space, quietly. Its seasons change slowly. Its weather shifts gradually. Voyager 2 is the only spacecraft to have flown past. In 1986, it passed by Uranus, capturing images, measuring fields, revealing basics. But since then, no mission has returned. What we know is partial. Models fill the gaps. Simulations extend the data. But Uranus remains, in many ways, the most mysterious of the outer planets. As we continue outward, the light thins. The sun is now a bright star, still the brightest in the sky, but no longer a source of warmth. The solar wind weakens. The interplanetary medium cools. Neptune lies ahead, the final planet, slightly smaller than Uranus, but more massive, denser, and more visibly active. Neptune's atmosphere is a deeper blue, its bands more defined, its storms more pronounced. It radiates more heat than it receives. Internal energy that drives weather fuels winds that reach nearly 2,100 kilometers per hour, the fastest in the solar system. Like Uranus, Neptune has a slushy mantle of ices and a small rocky core. Its magnetic field, too, is tilted and offset, generating complex auroral patterns and irregular field lines. Voyager 2 passed Neptune in 1989, discovering the Great Dark Spot, a storm system the size of Earth, which later disappeared. Storms on Neptune appear and vanish. Clouds form and dissolve. The dynamics are quick, despite the cold. Neptune's largest moon, Triton, is retrograde. It orbits opposite the planet's rotation, suggesting it was captured long ago. It is cold, yet active. Geysers have been observed venting nitrogen. The surface shows cantaloupe terrain, ridged and broken, shaped by internal forces. Triton may harbor a subsurface ocean. It may be slowly spiraling inward, destined to break apart or merge. Neptune has faint rings, narrow and incomplete. Arcs, not full circles, maintained by the gravity of nearby moonlets. They are hard to observe, even up close. Like Neptune itself, they are present without announcement. And beyond Neptune, the solar system begins to dissolve. The Kuiper Belt follows, a region of icy remnants, dwarf planets, comets, and objects not yet mapped. The sun's influence continues, but grows thin. Light takes hours to travel here. The heliopause, the boundary where the solar wind yields to interstellar space, still lies beyond. But from here the planets have ended. The major masses, the regular orbits, the family of known worlds, all lie behind. Beyond Neptune, the structure continues, but the clarity dissolves. The Kuiper Belt is not a wall, but a region, a wide cold zone filled with remnants. Icy bodies orbit here in slow paths, some tilted, some elongated, some still unnamed. They are not evenly distributed. They move in resonance with Neptune, or beyond its pull entirely. The most famous among them is Pluto. Once the 9th planet, now understood as one of many dwarf planets. It follows an eccentric, inclined orbit, sometimes closer to the Sun than Neptune, sometimes far beyond. Its surface is a mixture of nitrogen ice, methane frost, carbon monoxide. It has mountains made of water ice, glaciers that flow in slow cycles, plains with patterns shaped by sublimation and recondensation. A world in motion, but at a pace that requires decades to detect. Pluto has moons, the largest, Charon, is nearly half its size, locked in mutual tidal embrace. The other moons are smaller, irregular, spinning in chaotic resonance. This system is not a planet with satellites, but a double body surrounded by fragments. And Pluto is not alone. Eris, Haumea, Makemake, Sedna, distant, icy, slowly turning. These objects are part of the scattered disk, the extended Kuiper belt, the region that blends gradually into the Oort cloud. No defined edge exists. Only decreasing certainty, increasing darkness. The Oort cloud is hypothetical in form, but necessary in explanation. A spherical shell, extending tens of thousands of astronomical units, filled with trillions of icy bodies. Comets waiting for perturbation. Occasionally, a passing star or galactic tide disturbs their paths, sending one inward. A bright arc appears in Earth's sky, a comet with a long elliptical orbit, traced back to a distance far beyond any known planet. These comets are visitors, not inhabitants. The sun even here still exerts gravity, but its light no longer warms. It marks direction, not illumination. Its influence fades into the interstellar medium. The heliosphere, the bubble carved by the solar wind, stretches outward until it no longer pushes back the galaxy's presence. This boundary is the heliopause, a membrane, not a wall. The Voyager 1 and Voyager 2 spacecraft crossed it in 2012 and 2018 respectively. They still send signals, faint and slow, powered by the decay of plutonium, moving further each year. They carry instruments, messages, memories. They do not see. They record fields, particles, space. They listen to the change in background. Inside the heliosphere, particles flow outward from the sun. Beyond it, the particles come inward from the galaxy. The interstellar medium is not empty. It contains hydrogen, dust, radiation. It moves relative to the solar system. And as we pass into this region, the stars regain prominence. Constellations realign. The background becomes dominant. The sun becomes one point among many. Slightly brighter, slightly yellower, but no longer central. It fades into the field. The edge of the solar system is not a destination. It is a process. It is crossed not by reaching a coordinate, but by watching influence disappear. Magnetic field strength drops. Charged particles shift direction. The sun's voice, once clear, becomes distant, then indistinct. What lies ahead is not unknown. It is simply unstructured. Other stars, other clouds, other systems, perhaps, orbiting quietly, without announcement. The next nearest star system, Alpha Centauri, lies over 4 light-years away. At current speeds, it would take tens of thousands of years to reach, and yet the direction exists. The motion persists. Out here, time stretches. Motion becomes trajectory, not orbit. Everything continues, but the patterns are looser. Gravity still rules, but with greater patience. Back inside, the solar system turns on. The inner planets continue their tight revolutions. The gas giants complete their slow arcs. The asteroid belt drifts. The moons eclipse and transit. The rings cast shadows. And light still travels outward. Photons crossing billions of kilometers, carrying images of systems that never ask to be seen. We are now beyond all of them, not in distance alone, but in orientation. There is no up, no center, only background, only motion. The solar system does not end in silence. It ends in merging. Its structure dissolves into that of the galaxy. Its rhythm blends into the larger rotation of the Milky Way. It becomes one system among billions. A layered complexity of rock, gas, ice, dust, and heat, held briefly in balance, then allowed to fade into other forces. And in that fading, it becomes more than a map. it becomes a memory of order, a pattern built on gravity, temperature, and time. A story not of destinations, but of scale, of variation, of balance. The grand tour ends not in conclusion, but in diffusion. The way light ends not in darkness, but in distance. What remains is not the structure, but the trace of movement through it.